We're talking about functions as objects within a set and looking at the different operations you can perform on functions. And here's the special notation you need. So first I can add functions, and if I add functions it looks like open parentheses f plus g close parentheses of x, and it's the same thing as just adding the two functions. I can take a difference of a function by replacing that plus sign with a minus. I can take a product by replacing the minus sign with the multiplication. And I can take a quotient by just putting in a division symbol, in this case the vinculum, inside of those parentheses to define the division of functions. Now for quotients, you have to specify the domain because g of x cannot equal 0. And so I can add, subtract, multiply, and divide functions just like I can numbers, and here's how I write it in function notation. Now there is a special operation on functions called the composition of functions. So a composite function is the function whose value at x is f of g of x, and it's called the composite of f and g. And it's read f of g of x in this case. And a note on notation, in case you don't like the nested parentheses, you can write it with a little open dot. Make sure that is an open dot in this case because that is the symbol for composition. And do not mix it up with the product, which is the standard closed dot. Now, the way to think of composite functions, it's like function inception, meaning a function put inside of another function. So that's what a composite function is. So with these 5 operations, let's look at an example, or a series of examples. I have f of x equals 3x and g of x equals x cubed, and I want to find the sum, the difference, the composite of f and g, the composite of g of f, and a composite of f, which you can totally do. You can put a function inside of itself. So why don't you try those, and then you can press pause or whatever, and when you come back, let's see what you should have gotten. So the sum and the subtraction are fairly standard. I just had to take function of f, function of g, 3x, and x cubed, and add them together. And of course I like these written in standard form, so I just rearranged the order. And then when I subtracted f from g, so it's x cubed minus 3x, which is just x cubed minus 3x. So let's go over the composites, and when you have to make a composition of functions, you have to work from the inside out. So that means I'm going to plug g of x into f of x. And so wherever I had x in f of x, which was just 3x, I have to plug in g of x, which is x cubed. So then I just get 3x cubed. Now if I swap the order and say g of f of x was just 3x, g of x is a cubing, and so I get 27x cubed. So the order of the composition usually matters, and I can actually make a whole bunch of composites. I can make f of g of f of g of f of g of x if I wanted to. But no matter how many functions you have composited together, you remember you work from the inside out. Now when I composite a function into itself, like f of x, that means I'm going to plug 3x into 3x, and I end up getting 9x. Now, composition is an operation of functions, and like most operations, there are identities. So the identity for function composition is this function right here. It's I of x equals x, because if I plug in I of x into some function, or if I plug in f of x into I of x, I'm going to get just f of x out. Now let's look at these two functions, f of x equals x minus 4 over 3, and g of x equals 3x plus 4, and these were chosen for a very specific reason. So let's find the compositions, f of g of x and g of f of x. So f of g of x means that I'm going to plug in g of x into f of x. So wherever I see the x in f of x, I'm going to replace it with g of x. So I have 3x plus 4 minus 4 all over 3. And when I simplify this, I get 3x over 3, or just x. Oh hey, check it out, that's the identity. I wonder what's going to happen when I composite g of f of x. And so same deal, I'm going to plug in f of x into g of x. And so g of of x is 3 times x minus 4 over 3 plus 4. And when I simplify that, I get x minus 4 plus 4, or hey, x. And when I talked about compositions, and I said that, if you did them different directions, most of the time it makes a difference. F of g of x and g of f of x are not necessarily going to be the same. Well, this is the case where they are the same when the output is the identity. This f and this g are very special because when you composite them together, you get the identity, and when you perform an operation and it yields that operation's identity, what you get are inverses. So we're going to talk about inverse functions now. So here are the rules for inverse functions. F and g are inverses, meaning they undo each other and yield the identity. If and only if f of g of x is x and g of f of x is x. And remember, these x's were the identity functions for composites. And over here, I'm just saying that it's only true for every element of the domain of g, and this is true for every element of the domain of f. And there is, of course, special notation. Many of the inverse functions are different kinds of functions that have names, but in general, if I just have some function f and I want its inverse, this is how I write it. I write it as f to the negative 1 power and then in parentheses x, and this is read f inverse. So raising it to the negative 1, raising the f to the negative 1 denotes that I have an inverse of f. Now, graphically, what's special about inverses is that they are mirrors of each other through the line y equals x. And so let's look at that example of f and g that we had earlier using GeoGebra. So I have my function y equals 3x plus 4, and I have its inverse here, and these are the two graphs, and if I look at the graph of y equals x and show it as a dotted line, you'll notice that if I take the red function and I reflect it through that line y equals x, I get the blue function. And that's the one graphic property of inverses, is that they are reflections through the line y equals x. So graphically, you can figure out an inverse by just reflecting points through y equals x. Now, in general, for functions that are inverses of each other, if f of a equals b for one function, then its inverse, if I input the b into the inverse function, I'm going to get the a out. So this is true for all inverses, and it's the only way inverses can work because they kind of undo each other. Now here's a very important note about inverses. Not all functions have inverses, okay? Because remember, graphically, they are mirrors about y equals x, right? So graphically, I have to check if the reflection through y equals x is a function. So a function does not have an inverse function unless graphically the reflection through y equals x is also a function. So let's look at this example, the classic parabola y equals x squared. And I have the line y equals x, right? Hypothetically speaking, the inverse of y equals x squared would be x equals y squared. And graphically, you notice it is indeed a reflection through the line y equals x. Each of these points reflected over through the line give you the lines on the other graph. However, we say that y equals x squared does not have an inverse function because this y squared equals x is not a function. It does not pass the vertical line test. If my function, when reflected through y equals x, generates a graph that is not a function, we say that that original function has no inverse. I mean, yeah, there's a graph right there. That's totally the reflection of through y equals x, but this is not a function. Therefore, y equals x squared and every other quadratic is not going to have an inverse function. And the way we can tell that a graph is not going to have an inverse is by looking at horizontal lines. like y equals 2, and we'll see that y equals x squared hits that horizontal line twice. Now, when I reflect a horizontal line through y equals x, what I get is a vertical line. And when I reflect y equals x squared through y equals x, I get this sideways parabola that doesn't pass the vertical line test. And it's because there was a horizontal line that hit the original graph more than once, and when I reflect it, that horizontal line, or that horizontal orientation of points, becomes a vertical orientation of points. Now, here's the big deal about inverses. If a function is to have an inverse, it cannot have two y values or more than two y values for one x, or it must pass something called the horizontal line test. So the horizontal line test says that a function has an inverse if and only if every horizontal line intersects the graph in at most one point. So it's just like the vertical line test for functions, but it's the horizontal line test for inverse functions. Now, if you pass the horizontal line test, you are a function that is considered one-to-one, meaning each x goes to exactly one y, not more than one y, and each y goes to one x, not more than one x, just one x. So each x corresponds exactly to one y and vice versa, okay? And if I look at a mapping diagram, one-to-one correspondences look like this. Each element of the domain goes to one element of the range. And then you'll see the elements of the range go to a unique element in the domain. So there's not more than one arrow going to any one element. All the elements are separate. So this horizontal line test is a big deal for inverses. So when I ask you to find an inverse function, right, the very first thing you have to do is you have to check for that one-to-one correspondence. And the easiest way to do that is to just graph the thing on your calculator or Desmos or something, just to make sure that it has that one-to-one correspondence. To actually figure out what the actual inverse is, you of course can, one point at a time, reflect it through y equals x and then find that equation. Or you could just swap the x and y and then solve for y. And that process undoes whatever was done to the input value originally to give you your inverse. So let's just look at this example of y equals x cubed minus 8. Now x cubed minus 8 is not quadratic, it's a cubic. It's basically the cubic parent function shifted down 8. And if you remember what the cubic parent function looks like, it looks like this. And where that's actually a little smoother right there. And it does pass the horizontal line test. And so now I can find its inverse by swapping x and y. And so I get x equals y cubed minus 8. And solving for y now is going to undo whatever was done to that x and give me my inverse, which is the whole point of the inverse. It undoes, right? So I'm going to add 8 to both sides. And then I'm going to cube root. So I have the cube root of x plus 8 equals y. And that is my inverse. And if I want to test it, I can graph those two together to make sure that the reflection through y equals x is the other graph, or I can composite it and put this function back in there to verify that it does give me the inverse.